Okay, so call the proportionality constant big G. You can look it up in one of the covers of that book you're not reading. Okay? If you're not reading the book, you're trusting me too much. Think about it. Okay, right? There's your proportionality constant.
Is that Newton's gravitational constant?
Well, yeah, I think Newton kind of understood proportionality and said, yeah, we got this constant, right? And it seems to be universal as far as we can see. It works for the sun and the moon and we don't know for sure about the stars at Newton's time. We kind of do now. Galaxies seem to obey it. And if we didn't have a universal inverse square law, things would be really screwed up, and we pretty much assume, but all evidence points to the assumption being correct, that the thing is universal. It works everywhere in the universe, has the same value anywhere in the universe. So I was going to say it's universal after I wrote down the law, but now that you brought it up, I'm going to say it's a universal constant. So F equals big G times little m1, little m2 over r squared. Okay? Where r is a separation, m1 and m2 are the two masses. Also, we're assuming that these are point masses or they act like point masses. Okay? And we can be a little more specific about that after we develop a little bit more about center of mass and stuff, okay? But basically, any planet or star is very nearly equivalent to a point mass of the same magnitude, okay?
Is it not a point mass
At its center.
because it's rotating?
Yeah, points can't rotate, but rotation doesn't affect this. Basically what it comes down to here is if you got two gravitational objects that are spherically symmetric, with spherically symmetric mass distribution, then the force acts between the centers of the two objects, or the centers of mass of the two objects if not. Okay? So I don't want to get too specific about this. So right now, these are particles or particle-like masses. Okay? Particles don't have rotational energy. Okay, I just did a lot of things we've observed in lab, right? And they don't have extent. They're concentrated at a point so we know exactly where they are. Okay? Or particle-like masses, between planets and moons and stuff like that. Yeah, I could digress. You know, the center mass of the moon is really at the center, and neither is the Earth because of tidal forces and all that stuff. We don't want to talk about that yet. Okay? Make sense? Okay, there it is. And G is approximately 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So when you multiply this by a product of two masses in kilograms, you're going to have a kilogram squared here and a kilogram squared in the denominator of this and all that stuff, right? And you're going to be left with a Newton because you're going to have a meter squared in the denominator and a meter squared here, right? Okay? So that part of it's easy. Okay? Any questions? It's a pretty simple law. If you understand proportionality, it's really simple. Okay? And there are kind of reasons for the r squared, okay? It's like if you got a particle here, its gravitational effect is spread out over a uniform sphere with the particle at the center, okay? Well, the area of the sphere is proportional to the square of its radius. Okay? If you understood proportionality, that would immediately click. But if you think of the formula, 4 pi r squared, which you probably don't know because, again, of deficiencies in requiring people to actually carry things in their heads. Okay? And if you do, that's great. And if you don't know how to derive it based on what you learned about surface areas in first semester calculus, second semester calculus, you're doubly deficient, because if it didn't click then, something that you didn't completely understand from geometry should click in first year calculus. Okay? Just tracing some things, some connections, the nature of some connections you really need to be able to make. And everybody that was in your position back when we actually had an educational system, you know, shortly after like the space race and stuff, they understand it in the rest of the world. You're competing, right? Fix that. Okay, anyhow, and fix our educational system while you're at it. That should just be a simple matter. Okay. Not really. Okay, so the gravitational effect being spread out over bigger and bigger spheres gets weaker and weaker. The spheres increase in area as the square of r, so that the influence increases as the reciprocal square of r. Okay? And that's not really a particle physics explanation of why it works. Okay? But it's a conceptual idea that's kind of close to reality. Okay? Okay, well, there we have this. There's our inverse square law. Now, we also have to know what direction these forces act in, don't we? Okay? So, well, I'll draw a picture off camera and then we'll come back.